So this week's main topic is chemical thermodynamics, and we actually spent quite a bit of time on chemical thermodynamics. In fact, when I taught this course years ago, this was actually a first semester topic, just because it's challenging. There's some math in here, and the math isn't too terribly difficult, but it's one of those things that you're going to have to take step by step, because if you don't do it step by step, it really won't work right. And I'm also going to include a few more things, particularly about a lab you're going to do, but let's get into the idea of chemical thermodynamics. So if you go back to 8th grade physical science, you remember that we really talked a lot about energy, and energy is defined as the ability to do work or cause change. And of course, there are two types of energy. There's kinetic energy, which is the energy of motion, and there's potential energy, which is the stored energy of position or composition. So if you think about a ball, think we got a roller coaster right here, and you have a ball at the top of the hill. This ball has a whole lot of potential energy. I'm going to just say it's infinite, even though it's not. And then the kinetic energy is zero because the ball is stopped. And as the ball rolls down the hill, when you get down to the hill here, all the potential energy has gone down and the kinetic energy has gone up. In chemistry, when molecules are moving, they show kinetic energy. We can actually measure it by measuring their temperature. And molecules also have stored energy because you need energy to hold chemical bonds together. So based on the way molecules are arranged, they have both chemical and potential energy at the same time. And we've talked a lot about the law of conservation of mass. We really have not talked about the idea of the law of conservation of energy. The law of conservation of energy states that in a chemical reaction or physical process, and a lot of times we're talking about phase changes here, so this is a physical process a lot of times, we don't create or destroy energy. Instead, energy just changes forms, either from kinetic to potential or potential to kinetic. What this really means for in chemistry, though, is that in a chemical reaction, if you break the bonds, you're going to release potential energy and make kinetic energy. And if you form new bonds, you're taking kinetic energy out of the system and putting it back in as stored potential energy. When you want to talk about phase changes, if we increase temperature, we have to add energy to the system from an outside source. So if you want to think about if you want to heat a pot of water, you're going to add energy from the stove. The energy comes from outside the system, and that energy adds the water. Adds heat to the water to heat the water up. If you want to decrease temperature, we have to remove energy from the system to rebuild these molecular forces that are between the molecules. So if you see, like, if you want to make ice cubes, you put water in the refrigerator or freezer, and eventually what happens is the energy leaves the water and the water turns to ice. Energy and heat are not the same thing. Energy is the ability to do work or cause change. Heat is just the transfer of energy from one location to another. If you want to melt ice in a lab, what you can do is you can transfer heat energy from the hot plate to the beaker, and that melts the ice and boils the water. There's also two things to talk about in a physical process: the system and the surroundings. So say you're heating a beaker of water. So there's my beaker, and here's my water. And if I put it on a hot, so this is going to be my system. Everywhere else in the universe, including the hot plate, anything else, that's the surroundings. So we transfer energy, we transfer heat from the system, which is this beaker of water, to the surroundings. Since heat is a form of energy, we measure it in the unit called the joule. In chemistry, the unit we're going to use for heat is the variable Q. And sometimes Q is written as big Q, sometimes Q is written as little q. It doesn't really matter. We're going to use the joule. The other unit we use sometimes for heat energy is the calorie. And the calorie has a really unique definition. The calorie is defined as the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. So that's 1 calorie is the energy required to raise water by 1 gram of water by 1 degree Celsius. So we have to talk about Q for a second. And if Q is positive, that means that the heat energy has changed. We put heat into the system. So if Q is positive, that means energy in. I'll write that so you can see it. If Q is negative, that means that energy came out. So if energy comes out of the system, it's actually getting colder. And if you put energy into the system, it's actually going to be warmer. Enthalpy is the measure of how much heat is in a system at constant pressure. And enthalpy is expressed as H for heat, but we often call it delta H, which is the change in heat energy, because the Greek letter delta means change. There are two ways in which the heat can change. If delta H decreases, heat leaves the system gets colder. However, just because the system gets colder, that means the surroundings actually get warmer. If delta H increases, heat enters the system itself gets warmer, and the surroundings get colder. And we're going to talk about why that's important in just a little bit. The other thing that's on this slide that's really important is this definition of the terms exothermic and endothermic. Based on whether the heat goes in or out, we classify a process as being exothermic or endothermic. So in an endothermic process, energy is added to the system. This means that delta H is positive. Okay, it's energy in. You can remember this because in and N for endo sound alike. So if you think about this graph right here, the reactants are down here with their energy level, the products are up here with their energy level, and you have to put energy in. This little hump is called transition energy. You may have seen it when you studied enzymes in bio. So that's why there's this little bit of extra energy right here. It's the energy that makes the reaction happen. Or sorry, it's called activation energy. I apologize. So this is our activation energy. It activates the reaction. Probably studied that in bio. It turns to transition state. But overall, it's right here, this delta H. This is how much energy you gained in the reaction. So the products have more energy than the reactants, and you had to put energy in. Because you're taking energy out of the surroundings actually feel cold. Endothermic processes feel cold. And the way I remember that is that endo has 4 letters, and so does cold. Exothermic processes are the opposite. In exothermic processes, delta H is negative. That's because you're taking energy out. The system is giving off energy to the surroundings. This time the reactants are up here. You still have to put in that activation energy to make the transition state, and then when it comes all the way down to products, the products have less energy. Exothermic reactions are the opposite. Exothermic reactions, because they give off heat, they feel hot, and once again, exo and hot have 3 letters. So some examples of exothermic and endothermic processes. These are some of the questions here. On a cold day, you open the hand warmer packet. The iron in the hand warmer reacts with oxygen in the air. It gets hot. Warming your hand, is that going to be an exothermic or an endothermic process? The answer is it's exothermic. The reason it's exothermic is because it feels hot. You're playing sports, and the trainer brings you a plastic ice pack. You crunch up the pack, ammonium nitrate reacts with water, and the bag feels cold. This is actually an endothermic process because it feels cold. So it's taking energy away from the surroundings and making the reaction happen. Ice melts into liquid water. So once again, you have to put energy in to do that. So energy in, this is going to be an endothermic process. In the exact opposite process, water freezes into ice, you're getting energy out. That's an exothermic process. And one of the things you should note is that the delta H value for both processes is the same. It's just the exothermic process is going to have a positive delta H value, and the endothermic process is going to have a negative delta H value. So this is kind of a weird slide, but the idea is because substances have the same chemical bonds and the arrangement of atoms and intermolecular forces, chemists have actually been able to calculate the change in enthalpy. So they've been able to calculate delta H for common processes of common substances. For example, we know how much energy water gives off when it freezes. We know how much energy water gives off when it boils. So these are the process of phase changes and combustions. We call these values standard enthalpies, and they're expressed in the terms of energy in either joules or kilojoules per mole required to change the phase or combust the substance at 1 atmosphere and 25 degrees C. It's not STP. It's just kind of what we would call almost like room temperature right here. So we know these values, and they're important. You'll always be given these values if you need them to solve, but we're given these standard enthalpies. We also have specific names for standard enthalpies. The standard enthalpy change of the melting and freezing point of any substance is called the heat of fusion, and it's expressed in kilojoules per mole. If you want to talk about the boiling slash vaporization or condensation process, that's the heat of vaporization, and it's also in kilojoules per mole. So for example, water has a heat of fusion, and it's written, it didn't copy this well on the slide, but we write it actually as delta H degree, and then fusion is like a little subscript down there. The delta H of fusion of water is 6.01 kilojoules per mole. That means if I want to melt ice, for every mole of ice I have to add 6.1 kilojoules of energy to the system. To freeze water, I have to take 6.01 kilojoules of energy out for every mole of water I have. The heat of vaporization for water is also similar. Once again, it's written kind of funny, but delta H of this is 40.7 kilojoules per mole. So it's a lot more energy to boil slash condense than it is to freeze and melt. Okay, so knowing all this, we're actually able to solve problems. And some of these problems are tricky, but they're not so bad. So we have 4.75 moles of ice. What we know is that the heat of fusion, so we write delta H of fusion is equal to, and we saw this on the last slide, 6.01 kilojoules per mole. So energy, which is Q, is equal to the heat of fusion times the moles, which is equal to 6.01 times 4.75. When I solve that out, the kilojoules per mole is going to cancel, and you're going to be left in kilojoules. So it's 6.01 times 4.75. And with sig fig, I'm going to get 28.5 kilojoules. So that's how much energy it takes to melt 4.75 moles of ice. On the other hand, we have how much energy is evolved when 250 grams of water condense. Notice that this time we don't have it in moles, we have it in grams, so it's an extra step to the problem. We have to take the grams of water, and we have to say I have 250.0 grams of water. And I know that, and this is going to be a rough estimate here, but I know that grams of water for moles of water, this is 1 mole of water has a mass of 18.0153. When I solve this out, I get 250 divided by 18.0153. That's going to give me approximately 13.877 moles of water. So you have to put this into moles first. And then you know that the heat energy is going to be the heat of vaporization, because this is a condensing problem. The heat of vaporization times the moles, which is 40.7 kilojoules per mole times 13.877 moles gives me an answer of 3,469.27, but to simplify it, we're just going to call it 3,470 kilojoules. Then we've got to go back and make sure that we're correct here. So I had to put energy in to melt the ice, so this is fine, but since I got energy out in this one, this is actually going to be a negative answer because it evolved, so it's actually negative 3,470 kilojoules just because I got energy out of the system. So all of this is a phase change diagram. If there's nothing else to understand, if you don't understand the math and all this, this is fine. I need you to understand this diagram. If you look at this diagram, as I heat water, water starts off as a frozen block of ice right here, and it turns all the way to steam up here. When I first add energy to the ice, it gets hotter and hotter and hotter. Then, as it changes phase, notice that the temperature doesn't change. It stays similar for a while. It stays right at the 0 degrees, which is the freezing point of water. It stays that way until all the ice has become water. Then it heats up again. Then it stays the same when it's all changing to gas. Once it's all changed to gas, it can start to heat up again. So really, if you understand this, it doesn't change temperature when it's changing phase. No substances change temperature when they change phase. This is what it says. In regions A, C, and E, as we add heat energy, so we're increasing enthalpy, delta H is going to be positive. Temperature is increasing, so the energy we're adding is being used to increase the kinetic energy of the ice or the water or the vapor molecules. That's what's going on here, here, and here. In regions B and D, when we add heat energy, so we're increasing enthalpy, so once again, delta H is still positive. The temperature doesn't change. What it means is that the heat energy is being used to increase the potential energy of the molecules. In other words, we're breaking intermolecular forces here so the molecules can move faster. That's why the temperature doesn't change when we change phase. So change phase is no change in temp. And if there's nothing else you get out of this, like I said, when substances change phase, they don't change temperature. I'm going to say no temp change. So sometimes when I add energy, I'm not changing phase, I'm just making the temperature hotter. And what I'm really doing is increasing kinetic energy. Temperature is a measure of the average kinetic energy of the molecules of substance. So if I add energy, I'm going to change the temperature. Different substances, however, have different intermolecular forces. So it takes more energy or less energy to change the temperature based on the substance. Specific heat is a value that is the energy required to change the temperature of a substance by 1 degree Celsius. 1 gram of a substance by 1 degree Celsius. So we write specific heat in the units of joules per gram degree C. You could also write it in calories because we sometimes use calories as well. And the variable is C, so it's C for specific heat. The stronger the forces in a substance, the higher the value of C. Also, different phases have different C values. So if you look at water, ice, and steam right here, water actually has the strongest intermolecular forces when it's a liquid. That's why its specific heat is higher. It takes more energy to change the temperature of liquid water than it does ice or steam. Likewise, it takes more energy to change the temperature of water, which has these hydrogen bonds, than alcohol, which just has kind of weak dipole or London dispersion forces. So knowing about specific heat, we can actually calculate the heat energy required to change the temperature of a substance. And it's a factor of the specific heat capacity of the substance, the mass of substance you have, and how much you want to change the temperature. And we have this equation, which is Q equals mc delta T, where Q is heat, M is the mass of substance, C is the specific heat capacity of the substance, and delta T is the change in temperature, which is sometimes expressed as TF minus TI. And what you'll notice is that if TF is greater than TI, this is going to be positive, which means Q is going to be positive, which means that it's going to be exothermic. Energy's got to be put in. If TF is less than TI, it's going to decrease in temperature, which means Q is going to be negative, which means energy is going to come out, and it's going to be endothermic. So TF minus TI determines quite a bit. So let's do a couple of these problems. They're not quite as challenging as the other one. So let's say we have how much heat energy is required to change the temperature of 37.3 grams of aluminum from 11.7 degrees C to 185 degrees C. We're actually going to have to go back and use the chart and look up the specific heat capacity of aluminum. When we look it up, we see that aluminum has a specific heat capacity of C equals 0.897 joules per gram degree C. It's really important, though, to know that I would really give you these numbers on a difficult problem. And then it's a simple problem. We have Q equals MC TF minus TI. And then it becomes Q equals 37.3 grams times 0.897 joules per gram degree C. And then TF minus TI is 185 minus 11.7 degrees C. Remember, we solve sig fig at the end. So this is actually going to be 173.3 degrees C. And when I solve this all out for a total, remember our final answer is going to need 3 sig fig. I get 37.3 times 0.897 times 193 or 173.3, and I get 5,798.288 joules, which rounded to 3 sig fig and solved for kilojoules is 5.80 kilojoules. So that's how much energy is required there. And then this last one says if 492 joules of heat energy is added to 65.0 grams of iron at 27.2, what will the new temperature of iron be? And this is a little bit more challenging because it's 2 steps. So we have Q equals MC delta T, but we're not actually solving for delta T, we're solving for Q, we're solving for delta T here because we want the new temperature. So if I know that Q equals MC delta T, then delta T, rearranging the formula, is Q over MC. Then I solve it. I have 492 joules over 65.0 grams. And then I looked up the specific heat of iron. It's 0.449 joules per gram degrees C. When I solve that all out, it's 492 divided by 65 divided by 0.449. It's 16.8579. Then I know that delta T is equal to TF minus TI. So I know that from here, 16.8579 is equal to TF minus 27.2. Solving by adding 27.2 to both sides and solving for sig fig, I get that my answer on the final temperature is going to be 44.1 degrees Celsius. This last one is the hardest problem of all, and it's actually really helpful if you solve it. You've got to put this all together. So a couple things we're going to do first. It says 500 milliliters of ice are sitting in a beaker at -4 degrees Celsius. How much energy is required to turn this water into steam with a temperature of 111 degrees Celsius? Before I do anything, I need to put this into both grams, because remember we have milliliters, and moles. But I know that 500 milliliters of water is equal to 500 grams. And then using stoichiometry, so there's one answer. Using stoichiometry, I can say grams of water, moles of water. I know this is 18.0153 in 1 mole. It's also going to equal 500 divided by 18.0153. It's going to equal, let's just say, 27.6 moles of water. So we have these two values, and they're going to be important later. The next thing we're going to do is we're going to think about what this graph tells us. So if you remember our graph, we kind of have 4 regions. We have that 0 phase change, it's 100 phase change. So what we're doing here is we're going from -4 to 0, changing phase, 0 to 100, changing phase, and then going finally from 100 to 111. So it's actually a 5-step problem, and you have to add a lot of this together. So the first step is -4 to 0. So we're going to call this region, we'll use gold, we're going to call this region A. So this is how we solve region A. Region A is a Q equals MC delta T problem. We know that we have 500 grams. This is water as ice. So water as ice has a specific heat capacity of 2.03 joules per grams degree C, and we're changing it a total of 4 degrees, from -4 to 0. When I multiply that all out, I get 500 times 2.03 times 4. I get 4,060 joules. And then we're going to do region B, which is this phase change region. Now remember, the phase change region is different. The phase change region is Q equals moles times delta H of fusion, which in this case is 27.6 moles times 6.01 kilojoules per mole. When I multiply that all out, 27.6 times 6.01, I get 165.876 kilojoules. So that's the second number we need. Then we've got region C, which is this next phase change region, which is Q equals MC delta T again. See how this gets repetitive? It's 500 grams times, and this time the specific heat is 4.184 joules per grams degrees C. Delta T, we're changing it 100 degrees. And when I solve that all out, it becomes 500 times 4.184 times 100. I get 209,200 joules. Notice that some of these are in joules and some of these are in kilojoules. Let's go to the region D. Region D is a phase change region. So we have Q equals the moles times this time the heat of vaporization. So the delta H of vaporization, which is 27.6 moles times 40.7 kilojoules per mole, which is going to be a lot. So 40.7 times 27.6 is 1,123.32 kilojoules. Notice the black ones are in kilojoules. And then finally, this last little bit of phase change, region E, is another Q equals MC delta T, because we're changing temperature, not phase. So we have 500 grams. This time it's steam, so steam is 2.01 joules per gram degrees C. Change in temperature, this time we're just going up 11 degrees Celsius. And when I solve that all out, it's 500 times 2.01 times 11. It is 11,055 joules. So finally, the last step is to add all of these together, but we have to make sure that we're putting them in the same unit. So let's just use kilojoules. So I have 4.060 kilojoules plus 165.876 kilojoules plus 209.2 kilojoules plus 1,123.32 kilojoules plus 11.055 kilojoules. And when I solve it all out, I get my final answer of 1,513.511 kilojoules. Solving for sig fig, we're going to go with 3 sig fig because that's what we started the answer. There's a lot of multiplication here. I was just going to say 1,510 kilojoules, and that's quite a bit of energy, most of it being spent just in this region here where we needed to change the phase to steam. So that's a whole lot of information. What are the big takeaways? The big takeaways are what is heat, and it's the transfer of energy. What is an exothermic reaction? It's energy in. It's going to feel hot. I should say in feels hot. And we know that Q is positive. Endothermic reactions are energy out. They're going to feel cold. Q is negative. The other thing we need to know is calculating Q. Remember, for phase changes, we have to be in moles. And we use the heat of fusion or the heat of vaporization. For temperature changes, we use Q equals MC delta T. So normally we spend a lot of time doing these problems. They're not super challenging once you get the hang of it, but this is a lot for right now and a lot for home. So instead, we're going to spend the last little bit of this doing a lab on calorimetry, which kind of takes us into a real world application and lets them solve the problems for you.